So welcome to the eighth semester. So now in this semester, we are going to study about the elective number 4. The subject is low power VLSI. The subject code is 4BEC 741. So this is the subject code. So to enter into this subject, so you need to know something like what are things the prerequisite is required to study about this subject. The basic about your simple I can say the basic CMOS VLSI is required to study about the low power VLSI as you have studied in the fifth semester and in the sixth semester. I hope you might have studied the basic CMOS VLSI and the digital VLSI design. Now let us start with this. So in this presently for the module 1, what and all we are going to study. First, let us put the foundation as like what is the introduction about the low power VLSI, or we can say the VLSI, then low power VLSI, the why low power VLSI. Next, let us study something about the structure of MOSFET. That here shortly here I'm given as MIS structure. The MIS stands for metal insulator semiconductor. So that is a structure we'll study. We need to study about the equilibrium, like the flat band, about the Fermi level concept of MOSFET that we have to study here uh, on different modes of operation. Next, we will study why low power, then what is the need of low power VLSI design. Then let us do little bit small derivation about the threshold voltage derivation. Then here we are going to study about some of the effects like long channel effect and short channel effect. So in the long channel effect, actually we are having some two different types of effects out there. The one is channel length modulation, the another one is the body effect. But here we are going to concentrate on body effects. The second thing is we are going to study about the short channel effect. So the listed short channel effects are the surface scattering, punch through, velocity saturation, impact ionization, and hot electron effects, the drain induced barrier lowering, that shortly we can call it as DIBBLE, then narrow width effects. So these are the things we are going to study. So now before enter into that, what we will do, let us go for something like what is the evolution of the IC era. We need to know what is the evolution of the IC era in the sense like from the beginning that during the year 1947 the transistor was invented. So we can say transistor was invented that during 1947 there is a component, only one component, that is the transistor. Next, what happened? They went to the discrete components were, that is the I think by 1950 to 1960 the discrete components were invented, or it has come in the market like which are the product example if I want to say, like the diodes like a PN junction diode, then a Zener diode, and the transistors, the BJT, like NPN BJT, I can say BJT, or I can call it as a FET also we can say. So those things has come in the year during 1950 and 1960. Later what happened? So they segregated the IC era because these two are like the components. Then what is meant by IC? As you know very clearly, that is integrated circuit. What is meant by integrated circuit? The integrated circuit is nothing but the more number of transistors are accommodated in a single circuit, in a single chip. That only I can call it as integrated circuit. So now that will be categorized as by like SSI, then we categorized as MSI, then we'll go as LSI, then we'll go as VLSI, then we can go as ULSI, then we'll go as GU VLSI. or GVLSI. So these are the different categories are there where the SSI stands for small scale integration that has come in the period of 1961 to 1965. So what the small scale integration says, that is nothing but in a chip, or I can say, so out of 10 to 100, the transistors are accumulated in a single chip. That only we can call it as small scale integration. So what are the examples we can say in this? In simple, I can say the logic gates. Then we can say flip flops also. You just remember in your CMOS VLSI, you might have studied logic gate. You might have implemented two input NAND gate, two input NOR gate using CMOS. So if you want to implement any logic gates with the help of CMOS, then how many transistors are required? Yes, this is a question for you. If you are going to implement a n input logic gate, then how many transistors are required to implement a n input gates? N input, any gate you can take, either a NAND gate, NOR gate, any n gate, all these things. How many transistors are required for n inputs? I need the response. Just think and tell. Anyone can say the answer. Yes, Anish? Anish, tell me how many transistors are required to implement a N input with the help of CMOS? Bindu, I need the answers. So to implement a N input logic gate with help of CMOS, totally we require 2N transistors are required to implement. What is the 2N, where the N is nothing but a number of inputs? Say example, you consider you are going to implement a 2 input NAND gate. So for two input NAND gate, so you need exactly the equal number of the P transistor and the N transistors required. So two P transistors and two N transistors are required. So I can say the number of input is 2. So 2 into 2, totally 4 transistors are required to implement a two input NAND gate or a NOR gate. Similarly, if you are going for any n number of inputs, then this will be the formula, as you know that. So it's like a 2n transistors are required. Similarly, for a flip-flop also, when you're going for to implement, then we go for the next, the category is a medium scale integration. So what is a medium scale integration that has come in the year during 1966 to 1970? So how many transistors will be accommodated in a single chip? It is like the range will be from 100 to 1000 transistors will be in a in the single chip. So the examples are I can say decoders, the encoders, the multiplexers, counters, and the adders. So all these things will come under a medium scale integration. This is what you studied in your digital logic integrated circuit. So initially you might have studied logic gates. So later what's happened with the help of the logic gate, you might have designed the uh, decoders, encoders, multiplexers, demultiplexers, counters, then adders, all those things. So now the next category is large scale integration, that is LSI. That has come in the period 1971 to 1979. So how many the number of the transistors will be accommodated in a single IC? Like from the range will be 1000 to 20,000 transistors can accommodate in a single IC. So the examples I can say it's a memories, simple memories I can say like read-only memory, random access memory, that is RAM and ROM. Even I can add a 8-bit microprocessor. That is a initial microprocessor. That is 8-bit microprocessor in the sense I can say it is nothing but a 8085. So those also will come under the larger scale integration. Later, what happened? It has come as VLSI, that is very large scale integration circuit. So our subject is low power VLSI. So we are here actually. So very large scale integration. So that has come in the period 1980 to 1984. So now how many number of transistors are accommodated in this in a single IC? That is from 20,000 to 50,000 transistors can accommodate. Actually, this is numbers is given. Even I can say 20,000 to 1 million transistors. Also, I can say it is not exact. Actually, it is something like approximate. So what is it in a single IC? So around less than 1 lakh, I can say simple 1 lakh transistors can accommodate in a single IC. So what is the example I can say? The examples are it's like a 16-bit microprocessor, then 32-bit microprocessor, then DSP, that is a digital signal processor, then RISC processor. So those things and all will come under the very large scale integration. Next, after 1985, like it has come like ultra large scale integration. It is more than 1 million transistors can accommodate in a single IC. So that is nothing but a 64-bit microprocessor or dual core microprocessor. Like now presently we are not in like ULSA I can say, or simple one more also as I mentioned, GU, that is GU VLSI I can say, that is giant ultra large scale integration. That is more than simple I can say. If I want to say ultra large scale integration example, 64-bit dual core and all we said. Another example, so I can say the sensors also will come in the ultra large scale integration. Then the supercomputers, so that's also will come in the ultra large scale integration only. So these are the some evolutions of the IC technology. So now we need to study about like in the low power VLSI. First, before we enter into the low power VLSI, so what are the three like factors, the very important factors? Just you imagine in the previous days how the electronic circuits are manufactured in the like very olden days. If we say like if I want to consider that example, you take it a computer. So in the earlier days, so the computer, if you want to keep a one computer, one large room is required to keep one computer. That much the size is very big. Now, when you are going to fabricate or when you are going to design in one IC, what are the key factors you need to keep in your mind? So simple, I can say like the important key factors to design a one IC is here. Like in if you consider a VLSI, so these are the very important factors. That is nothing but the area, power, speed. Without these three common factor. This factor actually, so we never design or we never fabricate a IC. So all the specification they will be concentrated on any of these parameters. But if you are going to design a IC, you cannot implement all these three constraints in the sense you cannot able to satisfy all the three factors like area in the sense so simple I'll say you are going to design a one simple one device electronic device so area in the sense the size of the gadget or the device should be our ultimate aim will be what that it should be small okay area should be small okay that is less what about the power that is the power consumption will be less we need what about the speed will be more that is speed should be high or I can say this directly I can say your delay should be very less so when you're going to design a circuit these three factors we need to keep it in mind but the problem is all these three factors you cannot satisfy. Say example, you are going to buy a one laptop. So if you're going to buy a one laptop, so even you may think the size of the laptop should be very small. Okay, next your power, like the battery backup. The battery backup it should have more backup you may require. At the same time, the speed is should be very high. But all these three you cannot get. There will be some trade-off between some of the factors. So you can concentrate two factors actually. So any one key factor you need to sacrifice. So you cannot able to concentrate all the three factors. So example, if you are going to concentrate on area and speed, example, the area into speed, if you are going to concentrate, then you need not to worry about the power in the sense you should not worry about the power because you are going to minimize the area, you need to improve the speed of the circuit, then automatically power will be like more in the sense, simple I can say, the power consumption will be more like so at the same time if you want to concentrate on like area and the power then you should not worry about the speed so like this there will be trade-off so nowadays in the present scenario if I see because the power consumption is one of the very big challenge in a modern day VLSI design. Why? Because all the portable devices nowadays it is run on a battery power. That is why the low power has come into the picture. So because earlier and all, we doesn't have that much low power concept. So the design, but later now what happened? So the day by day, nowadays in the modern era, so all your electronic gadgets or the electronic devices or the ICs, everything becomes like very very small at the same time. We need it will be operated in a battery. Nowadays you can see you might have seen example your cellular mobile your mobile phone. If you see a mobile phone, the mobile phone will be operated with a battery. So very important thing you see that the battery will have very, so you might have seen internally you go and see how much the power, the rating will be the ticket. So the operating voltage will be around 5 volt or 3.3 voltage only. Say that much. Like if I use one battery, so you no need to charge your mobile phone for 24 hours, even though you are doing operation is more operation performing. So that is a concept like you need to what more to do that like the power consumption like so at the same time you can see your device size will be big actually next what about the speed the speed will be a little bit slow so that is why you can say you can take the nowadays all the devices so one or the other problems will be there nowadays all the companies which are the companies the semiconductor companies if I say like Intel then Philips, then Samsung example, then Apple, Apple company. So these companies are they are having their own fab city. Fab city in the sense the fabrication. They are having the own fabrication unit. They are having actually, but as of now in India, we doesn't have any fabrication unit. So in our India, we're not doing any fabrication. So we are buying the silicon wafer from the abroad, from any like apart from the India. Not we are not fabricating in India. So like now, the presently the work is going on to set up the fabrication because the cost is very high to make a setup. Now, in this, there will be various stages will be proposed to control the power dissipation. So, for that only, we are going to study elaborately, but more elaborately, like what are the techniques, what are the different types of power dissipation is there. Then, if we are getting the power dissipation, then how we can overcome or how we can try to avoid those power dissipation with the help of some of the techniques. So these things sometimes we are going to study in this low power VLSI design. So now here we know that in your CMOS VLSI you might have studied something called as there is a one thing that initially there's a person, the name of the person is called as Jordan Moore. Jordan Moore. So you know who is this person? Do you aware of this person? Jordan Moore is the founder for which company? Is a founder for Intel. Okay, so he initially what he proposed the Jordan Moore in the sense because initially if you talk about the computer in the sense Intel is the first company that has brought up the computer to the market like the processor example that is nothing but a first initially they brought a 4-bit like one simple calculator like to perform an arithmetic operation they brought one simple IC actually then later to commercialize in the market like they brought initially simple 8085 microprocessor that is 8-bit microprocessor to perform some simple operation initially the Intel only they brought. So what happened like one more thing I need to ask here like we are studying about the IC integrated circuit IC right. So who developed this IC and you know then what is the name of the person IC who developed the IC who is the person behind this to develop the IC he is a person is a founder of Texas Instruments. Texas Instruments. What is the name of the person? It is Jacob Gilby. So he is the person, the first developed brought the IC like we can accommodate 5 to 10 transistor initially like 10 transistor in a single IC. That is why the initially you might have used in your digital design lab like AND gate IC, OR gate IC. Then in your circuits lab, say example if you want to say operational amplifier IC, operation amplifier. So those things all has come in the initial stages. So now, okay, let us come to the Moore. What this Moore suggested in the market in the initially, like he said, for every 18 months, the number of transistor will be doubled in an IC. That is what he suggested earlier. Means what he suggested is for every 18 months, the number of transistors will be doubled in a IC. That only later will called as Moore's law. You might have studied in VLSI, the very basic VLSI, Moore's law. What is Moore's law? The Moore's law states that for every 18 months, the number of transistors will be doubled in a IC. So that only it will be accommodated. But you think now you need to think something like the number of transistors is getting increasing. Okay. Now you think about this is my IC. This is my IC. But initially now, as I mentioned, the number of transistors will be doubled for every 18 months. You keep it in mind. Okay, like every 1.5 year. So now the for first initially say example, if the transistor is 10, okay, after 18 months, what will happen? The number of transistor will be 20. So example, the 10 transistor you are going to accommodate in this IC now. After 18 months, what happened? There's again the 20 transistor we need to accommodate in this IC. Now you tell me like 10 transistor we accommodated already. Is it possible to accommodate 20 transistor now in a single IC? After that, again 40 transistor, 60 transistor. Now you see the size of the transistor is nothing but 5 into 5 mm. Example, I'm saying this is 5 cross 5 mm. In the 5 cross 5 mm in the dimensions of the IC, you see 10 transistor, next to 20 transistor, next to 40 transistor, next to 80 transistor. Is it possible to accommodate? Is it possible? No, it's not possible because if you keep on adding the transistor, so from this one point is coming. If you're taking a one transistor, the very important, the factor, the key factor for the transistor is nothing but simple. It's a aspect ratio. That is nothing but W by L. That is the width of the transistor and the length of the transistor. So now, do you need to do this the scaling of the transistor? Then only you can accommodate in a IC. So as the number of transistors getting increases in an IC, so meanwhile time I can say your the scaling of the transistor will be reduced. So that you need to change it. So now you can see in this graph here initially like first during the 1990 that is 1900 to 1935. Here you can see here. So what this figure shows here, the x-axis, the year actually, the y-axis nothing but the calculations per second. How much the calculation will be done? Okay, like in like per $1,000 actually. Now you can see in this period actually what and all it's happened. Like see the analytic engine, tableter, the IBM tableter, the nationalist, all these things like electromechanical device up to 35. After 1940, actually what happened? The solid state relay has come during this year. Next year, 1945 to 1960, what happened? The IBM, they brought like some of the initial computers they brought with the help of the vacuum tube. Next to what happened? 1960, the transistor has come. After that, you can see here, this is everything is like IBM Pentium, everything is given. So just this is I put the platform, nothing, no need to worry about all these things. Then here you can see in this the year exactly we got the 1995 the Pentium has come. At the time only the computer has become revolution has become like everyone they started to use the computers, the Pentium 2, Pentium 3, Pentium 4 later at like core, dual core, quad core. Then now i7 core, i7, i8 like we got a still now core i11 has come now. Correct. So now presently, now as this increases, when you say simple, as a technology, I need to say. Now what happened to the technology? Like initially, like example, the technology was in micrometer technology. Correct. That micrometer technology went down to nanometer technology. This technology which indicates what? It indicates the length of the channel. As we know, if you are considering a one transistor, say example, you consider this is your cross section of transistor. Already you might have studied. This is the transistor, right? This is N plus. This will be your N plus. Then this will be your metal. Then this will be okay. See, this will be your gate, this is your drain, this will be your source. Now this will be your channel, right? So this is nothing but your L I will call. The L is nothing but the length of the channel. So example, if the length of the channel is 600 micrometer, now next what happened, that is brought down to like 300 micrometer. Next it has come to 150 micrometer. Then it has come to 90 micrometer. Then it has come to 60 micrometer. Then 45 micrometer. Then it has come to like again 180 nanometer, then 90 nanometer, then it has come 45 nanometer, then after that 22 nanometer, then after 22 it has come 18 nanometer. After 18 nanometer it has come like what, it's nothing but 14 nanometer.
10
After
nanometer.
after 14 nanometer, how much it
10
has come?
nanometer.
10
10,
nanometer has come.
10,
After
and
10, 7 nanometer has come. After
now
5,
3.
5
Now 3.
nanometer. Next is
3.
3 nanometer. Actually, if I want to say this 5 and 3 nanometer under progress now, actually, it's in on research. Even now, presently, the company, the Intel or some cadence company, they released, but none of the product is released. Still, the product is not released for the with the help of 10 nanometer actually. But you can see in this which technology they used. But as you studied, the technology which you used earlier, they you know that it's like a CMOS technology. But these all this technology, the CMOS is not involved actually. The CMOS was involved up to 45 nanometer only. After 45 nanometer, you should think if it is brought down to nanometer in the sense, you think about how your the length of the channel will be. Length of the channel, like see, this is the length of the channel. Is keep on is getting shrinking. If the length of the channel is getting shrinking, what is the advantage you'll get actually? So as we know that very simple, this is the length of the channel in the sense here. Here the electrons will be moved from drain to source. The current will flow from source to drain actually. So as the length is get reduces, what happen? So there will be the drift will be more, like the movement of electrons will be very fast, correct? So from this I can say, so it will improve or the delay will be less. So as it gets us very closure, so this nanometer, this is simple, I can say one uh, our human hair is there, no, one human, that is actually it's a nanometer actually. You think your the thickness of a hair, that is a nanometer actually. So that your length of the channel is like that only. So now very simple, the CMOS is not able to do this one after particular point of technology. 45 nanometer technology is not able to to shrink this. What happened later, the technology has come, the name of the technology is,
Gate all around field effect transistor.
yeah, so that is by simple I can say this is nothing but a FinFET. I hope you might have heard about that
An
FinFET.
advanced version of FinFET, sir, but the gate is completely surrounded.
Yeah,
So
the
there is
gate is
no.
complete. The fin is nothing but actually you will have the two fins will be there. Later, what happens? Still now, presently, the gate all over around it has come now actually. So still that work is going on. Actually, still it is not released.
Yes, sir. But they are planning to release by the end of this year, sir.
Yes,
Intel
yeah. So
and
still
few other
actually there is a testing is going on. Just only the wafer is released, but the product is not released. It's under the testing actually. There one more thing I need to say in this Lopo, like when you're going to design any circuit, the very important, the key factor is the testing. So if you want to test a simple, I will say you are going to design a one circuit. So if you are going to design a one circuit, if the input is 4 bit, assume 4 bit is the input in the sense, you take an example of your a 4-bit AND gate example. Okay, so you need to test your AND gate is working function properly or not. So at the time, what you need to do, you need to give all the 4-bit cases, 4-bit input in the sense around 16 combinations you need to provide. So all the 16, one combination, if you give when it just example I'm saying, if it is taking 1 nanosecond for to check one in one possible combination. So if it is 16 combination, you think about to check for all the combination, 16 nanosecond is required to check the functionality whether it is working fine or not. Now this is for only for 4 input. Now you think about now if we are going for a adder, say example, okay, one 8-bit adder. If I'm going for a 8-bit adder in the sense, you might have designed the 8-bit adder. So many different various types of adders are there. Say example, repeal carry adder, carry lookup adder, then Manchester carry chain adder, carry skip adder, then carry save adder. So many adders are there. So in this, any adder you take, okay, 8-bit adder. Now we need to perform a 8-bit addition. So 8-bit addition, if you're having two inputs like A, B, 8-bit in the sense, the total combination you are having as 2 to the power 8 to 256 combinations are there. So to perform one combination only based on the circuit, if it is say example for to compute one 8-bit combination only, if it is taking 20 seconds, example I'm saying 20 nanoseconds means then 256 you think about. Now you come for 8-bit microcontroller or you come for a microprocessor 32-bit or 64-bit you come. You see inside the 64-bit microprocessor how many the units will be there, then it has to check everything. Do you think it is possible? Do you think nowadays in the market all the electronic the components which is tested and it's coming with all the 100% testing? That is why if you go and buy any microcontroller in the market, outside market, then they will say they won't give any warranty guarantee, they won't give. But you may get the microcontroller, the 8-bit microcontroller with the cost of like 50 rupees. For 100 rupees, we'll get one microcontroller. How we are getting that? So simple, it is not tested completely actually. So that is the reason if you want to test, so it may take more and more year. So that is the reason nowadays electronics actually the cost also will be very high to test that. But the very important thing that test where they will do very high cost in the sense, example, if you take the medicals, if you go for a medical actually, it is very much essential. It must be tested properly because if not done properly, then that will give you more danger actually in the medical field. So that is why they are under for medical field, whoever, whatever the electronics, the chips, everything, it will be very, very more costly will be there in the medical field, especially. So now let us come to here our evolution of the low power. So now when you come for the evolution of low power here, I'm showing two things here. The one is nothing but the year, like this is a year. Then the power dissipation we talk about in terms of like the watts. Same here, as I already discussed, that is the scaling factor. So like your technology rule. Okay, so like what is the power density? Here you can see. So what happened as the year get increases here? What happened here? You can see this. Initially, the microprocessor unit was the operating voltage was VDD is 5 volt. So gradually, microprocessor unit later what happened? It has become as 3.3 volt. Same the DSP 5 volt, then 3.3 it has come. You can see here it is mentioned wherever the small bubbles these are the microprocessor unit. So this is your 3.3. See, this is you consider as like 87, 1987. You can see this place is 94. So after that, so from 5 volt to 3.3. If you reduce, there is the one concept like to low power. If your battery operator, I can say like or not a battery operator also the operating voltage I can say. So that will be like from 5 volt to 3.3 voltage it has come. Same for your DSP also. Now here you can see the scaling factor. The scaling factor will be here. You can see it's directly proportional to the k square, like linearly. See this? This is what happens normalized by 4 micrometer. This is like a factor k. Okay, so this will be your the power density of gates. So very important now. The very important from this overall, I can say Nowadays, what is our aim? It's nothing but all your equipments are operated in a battery. The second thing is I can say like you need to operate with the AC voltage like minimal operating voltage. So that is nothing but your power supply. Simple I can say the power supply only because battery in the sense even that is the power supply for the equipment. So even battery also will have like a 3.3 volt or 5 volt battery also will be there because the earlier time and all if you see that like you need to use like 15 volts or 20 volts will be there because if you see earlier TV and all if you see no we need to give the AC supply 220 volt but internally we'll have the regulator circuit will be there so that may give us like 20 volt or 22 volt it will give so based on that it will work but later what happened nowadays we are having a LED TV so for to work on the LED TV normally this 220 volt is not required even the 120 AC voltage but internally if you say like only 15 volt not even 15 volt like that is more sufficient to operate your TV so nowadays it has become in this way so after 1995 I think yes after 95 I can say after 1995 so the market or the company that started to look into the power issue actually because the earlier days and all they're not at all worried about the power they worried about only the area and the speed that is the delay of the circuit but later only what happened they are worried about the power also because of to miniaturize your circuit that is a very important thing they brought so next here if I want to say in your VLSI. In the VLSI, initially, I need to know something like you are having some two different designers there in the VLSI. The one is nothing but front end design. The another one is nothing but back end design. I can say. So another one more thing, if I want to put in the VLSI, two some factors are there. That is nothing but FPGA. The another one is called as ASIC. So can you tell what is FPGA? Anyone? What is FPGA? FPGA stands for Field Programmable Gate Array. So you are having, you might have studied so many programmable logic devices, that is PLDs they will call. Okay, so in that one of the family, like your Field Programmable Gate Array. Next, ASIC, that is I can call as ASIC. So what is the ASIC I can call? That is nothing but it's an application specific integrated circuit. Now, what is the difference between these two? This FPGA field programmable gate array, it's ready-made, it's available in the market. Just you can configure, or I can say you can reconfigure the architecture, or you can reconfigure the program in the chip. That is what now the presently so many FPGAs are has come. Like one of the simple FPGA, if I want to say, in the Xilinx, they given like one of the example I will say FPGA, the company which is given by the company is Xilinx. The name of the company is Xilinx. They are given. Then Altera company also they given like in the Xilinx they given that's initially they given like you might have used in the lab that is called as Spartan devices. Now presently we are having like something called as Vertex devices will be there. Next, as I mentioned, Altra, even those companies also they're having the FPGA. It is ready-madely available. Ready-madely available in the sense one simple concept if you want to say like we are having a ready-made IC, ready-made IC, that is FPGA. You are having, right? Now you are going to develop a one 8-bit microcontroller yourself. Example, this is example. So what you will do, you know the architecture of the microcontroller. You are going to write the programming. To write the programming like a very basic language for in VLSI for to describe the hardware. So I think, but it's a hardware description language that I can say is HDL. So it can be either it can be a VHDL or it can be a Verilog HDL. So any one of the language you can use, then you have to write the programming. So once you write the programming, next what you need to do, so that program has to be burned or it has to be dumped into the IC. So if you are dumping, that is why I mentioned like FPGA, like example. So you are dumping that 8-bit microcontroller into that IC, then you can use or that IC will be performed as a 8-bit microcontroller. Or if you want to erase that 8-bit microcontroller, use some around 8-bit adder, then that IC will perform as a 8-bit adder. But you need to design the IC for a certain specific application, for your own application. Then in market, the IC is not available. So further, what you need to do, you need to go for your own IC. That is why it has come as application specific integrated circuit. So what you need to do, for your own specification, you need to design a circuit. Then once you design the circuit, everything, so you can fabricate your own IC. So everything is done then, but when it comes to the under the cost, FPGA ASIC, which is more cost, the FPGA is very less cost compared to the ASIC. The ASIC will be very high cost. Now, can you know which the EDS to perform all these things? We need some software that is we can call as EDA tool. They'll call us EDA tool. What is the EDA tool? That is electron design automation tool. That is they call EDA tool. But later nowadays it has come as like CAD tool, the computer aided drawing tool. One of the computer aided drawing tool for electronic design automation is nothing but if you are going to perform a FPGA, then simple the software is I can say Xilinx is one of the software. Next I can call Mentor Graphics. Then I can say Altera. So these are the some the companies which is given for the FPGA part. But when you're going for the ASIC, so for ASIC actually, which companies given the software in the sense, the one is same I can say, like it is the one of the company called as Cadence. Cadence Design System, that is the one company. The second company I can call as Synopsys. Then one more company I can call as still we are having some Magma, then Cisco Mentor Graphics. Even these are the companies, some example. So if you want to work an ASIC domain. So here, one thing as I mentioned here, like in the ASIC also, you are having two different types, like two different types of levels of design is there. The nothing but one is nothing but a semi-custom level design. The another one is full custom design. So you might have heard about semi-custom design and full custom design. So what is meant by semi-custom design and a full custom design? Semi-custom design in the sense just you are going to fabricate your IC with the help of available resources library. Like simply if I want to say, if you are going to prepare a one dish, say example you consider as one biryani. If you are going to cook a one biryani. So what is that semi-custom level design? In the sense you are going to use all the ingredients which is available in the market, ready-made available, all the masala packets will get everything. Just your work is only to cook. That is semi-custom level. Okay. Next is full custom level. What is the full custom level? Full custom level, the same biryani you need to cook. But thing is, the masalas, whatever thing, all the things it has to be prepared by yourself. That is meaning is if for a circuit actually, you should create your own library for each and everything you have your own library. That one I can call full custom, fully customized by yourself. So now when I come for so difference like semi-custom and full custom if I say which is easy in the sense the semi-customs will be easy compared to full custom when you come for the after you design everything as I mentioned the cost wise the asset cost is very high because if you want to go for only one IC it will be very high cost but normally as you know in the market as the number of IC production cost is increases, then only the unit cost of your IC will get decrease. Say example, if you are going to fabricate a 100 IC, Say example, the one cost of each IC is 1,000 rupees. But if you are going to fabricate the same IC, the quantity as like 1 million quantity, then automatically then the 1,000 rupees will become as 100 rupees. So automatically as the number of the quantities, the production, the mass production if you do, then only the cost will be less. That is why in our market, the 8-bit microcontroller we are getting it outside, right? Simple market. So that is actually the mass production they will do. So that is why the cost is very less. Then that microcontroller also it is a FPG actually. It is not a ASIC. It's ASIC. Sorry, it's not FPG. It's ASIC because it's a 8-bit microcontroller. It's a dedicated to 8-bit microcontroller. Similarly, you might have used in your logic design lab like your multiplexers, then you might have used decoders. So those things also we can call as ASIC. It is application specific. It will perform only that operation. You cannot able to perform some other any other operations. That is what I can say. I hope I put some of the very basic, the platform or the foundations, it's like a little bit about the VLSI. So now when you're going to study the low power VLSI, now you're going to talk why we are going to study the low power VLSI because so many issues and so many challenges are there in the uh, circuits, in the VLSI circuit, especially when you concentrate on low power, so many the challenges will be there. So you need to take up the challenge, and we need to solve those challenge. So what are the various steps or various techniques will be there to reduce those things. So these are the things only we are going to study the further. But before that only we need to study simple about as I mentioned the very basic concept, the foundation that is metal oxide semiconductor field effect transistor we need to study. So that is what we are going to study in the later classes like the structure of MIS. Do you have any queries?